Hi, friends. Okay, so as promised, I'm recording the next one right after, so there won't be a wait. Lessons 14 and 15 were trusses 1 and 2. So going into method of joints and method of sections and how those will help you solve for the internal forces of truss members. So let's see. Method of joints. Okay. So I have 2 slides on methods of joints, right? One covers kind of the basics, how you do it, whatever, and then the next one has some like important tips. So method of joints. So essentially with trusses, you're going to have a series of members connected at the ends with a bunch of joints, right? So to find the internal forces of each member, one of your options is to essentially look at each joint and say, well, I know there's no net force or net moment acting on this joint, right? So by saying that, what you're doing is you're allowing for the, how would you describe it? You're allowing for the simplification of the overall system, right? So one thing that you can do, you don't necessarily always have to, it depends on what the question's asking, is you solve for the external forces, right? And that's something that you might not need to do, but it can't necessarily hurt you to do it. You know what I mean? The second one is to solve for internal forces. So internal forces are the forces acting in each truss member. So each truss member is a two-force member, right? So the direction of the force is going exactly in the direction of each truss member, right? So because you're looking at just one joint, every member that comes off of that joint intersects at the joint, right? Which means it's a concurrent system. So you only have two equations because all of your forces will have a perpendicular distance of 0. So that makes the moment equation useless. So you'll have two equations, some of the forces in the x direction, some of the forces in the y direction. And that's again because it's a concurrent system. So once you find that, you essentially look at as many joints as you need to solve for what the question's asking. So what you're going to do is you're going to break it up into individual free body diagrams and say, well, I know that the force at each joint has to be 0, right? So you essentially just do a bunch of some of the x, some of the y, solve for your unknowns. What's going to happen is you're going to have some unknowns on one joint. If you have a neighboring joint, the force pointing here will be equal and opposite. So if you're trying to solve for a force on this joint, but you have too many unknowns, solving for this one first if you can, you'll find this force, which you can translate over here and have one less unknown. Similarly, if you have one up here, you can move it down there. I can't even tell if you guys can see my video up in the top corner. So this might be a really stupid video. But essentially the point is, by sectioning it into individual joints, you'll be able to solve for forces that you can then substitute into another free body diagram if you need to. So because you only have two equations, the max number of unknowns you can have is 2, which means you're going to have to go joint by joint until you get to solving to get unknowns to substitute into another joint until you get to the member force that you are looking for. So it's super easy calculations because usually they're just like 3 or 4 unknowns, or between 1 and probably 4 will be the max unknowns that you see in a method of joints problem, right? It's just a matter of doing that same thing over and over and over again until you get to the joint with the exposed internal force that you're looking for. The second part is a continuation of method of joints, but it's just kind of a discussion on what it means for it to be a two-force member, right? So like I said earlier, a two-force member, the fact that a truss is truss member is a two-force member tells you that any force acting at a point will be in the direction of that member, regardless of what the direction is, right? So because of that, there won't be any like force up or force to the right, whatever. It'll be either pulling on the point or pushing on the member towards the point, right? So you'll either be pulling if that's the joint, you're either going to be pulling the member in tension away from it, or you'll be pushing the member into the joint in compression, right? So again, tension means pulling on the member, compression means pushing on the member. So because of that, uh, change in the actual structure of the force and how you're thinking about it, the way that your answer is going to look will change, right? So you're going to have whatever magnitude that you calculated for the force, you're going to have the units that the force are in, but instead of being up or down, it'll be in tension or compression. So that's the only change I wanted to really mention here. So trusses part, I guess that's part 2 because this was just part 1 continued. Or I guess not, I don't know. The third one is zero force members, right? So think about a bridge, right? So if you're driving on a bridge and you drive from like the road onto the bridge, you're going to be applying a force across the top of the bridge, which is going to cause it to shift. Ideally, minimally, because you don't want to fall, you don't want the bridge to fall, but you're still going to be applying a force. And because of that, you're changing the loading conditions on that bridge. So you have to have members on that bridge that are not useless, but are only useful in the event that the loading conditions change, right? So whether that be wind, whether that be use of the bridge. So in reality, if it's a busy bridge, like say the Skyway, I don't know if anyone knows the Skyway, but that's right by my house. So the Skyway Bridge in Florida always has cars going over it. So all of these, every member is constantly in use because the loading conditions always change. But when you're looking at a free body diagram, or when you're looking at like a truss in statics, essentially, it's a snapshot of the loading condition, which means there's no change going on in that instantaneous snapshot of that. So that means that all of the members that are built into the bridge for stability in the event of a loading condition will have no force in them because there's no change in the loading condition. So these members that are used for stability are called zero force members, because as you're looking at them in a free body diagram, there will be zero force acting on them. So that being said, zero force members are members that are added to a structure to add support under a varying load. And again, because the load is static in a free body diagram, the member has no internal forces. So the trick then becomes, so what's nice about zero force members is that if you can find them, you can really simplify the problem that you're looking at, right? Because you can essentially pretend that they're not there. The trick is just identifying them. So these are the two big rules that I would recommend memorizing, internalizing, and then practicing as much as you can, right? So the first case of identifying a zero force member, right, is by finding two non-collinear members that meet at a joint with no applied load. So literally when you're looking at a truss problem, pick a joint, count the members on it. If it's 2 and there's no forces on that joint other than those 2 members, both of those members are zero force members. So that's the first case. The second case is if at one joint, 2 members form a straight line and there's only one other member acting on that joint or applied at that joint, the other member, or the one that doesn't form the straight line, is a zero force member. So that being said, you kind of have to look at it a few times, right? So go through the entire truss structure a couple times, because as you're eliminating zero force members, so for example, say that you have a straight line and then two other members coming off of it. So you have essentially 4, but 2 of them are collinear, right? If you look at another joint and establish that one of those 2 is a zero force member from another joint, then you can essentially pretend that it doesn't exist when you're looking at that joint in this situation. So instead of the 4 with 2 collinear and 2 non-collinear, you have the 4 with 2 collinear, 1 non-collinear, and 1 zero force member, which essentially means that that has no use being in that drawing at all. So it simply or it essentially simplifies to this case. So that's why it's super, super important to look back at the structure several times, right? To make sure that by identifying one, you're not also identifying another one and just skipping it because you've already looked at that. So that's my advice. I literally looked at each truss structure 2 or 3 times easily. So the last section here is method of sections. So method of joints is super, super useful when they're asking for find the internal forces in each member, right? Because you can just start at the easiest joint and bounce all the way around because you care about every single thing. But most of your problems, because the idea is that the truss structures will get a little bit more complicated, most of your problems will only ask for the internal forces in one member or 1 or 2 members, right? So the idea behind method of sections is saying, well, if I only care about one member, I don't care about any of the other ones. So by cutting through that member and then navigating through to the other end of the truss, you're able to expose the internal forces that you care about without exposing every single other one that you don't care about, right? You're going to expose a few because that's the nature of solving a problem. You're going to have more than one unknown, hopefully. But you're going to essentially expose only, well, 3 or less unknowns by doing that. So the benefit is, or one thing to note, that when you're doing this, this should all happen after you look for your zero force members, right? Because a lot of times there is no clear-cut path from one side of a truss to another without crossing more than 3 trusses, right? So you have to check for zero force members because that won't count as an unknown. So you can cut through a zero force member without counting that towards your 3 unknowns. But that being said, oh, and by the way, I saw a lot of this in class the other day. When you're cutting a truss for doing the method of sections, you have to essentially, like, by making your cut, you have to be able to separate the bridge completely. So that means you can't, like, start at the top and then loop back around at the top. That would almost kind of be method of joints. You have to cut from the top to the bottom because you have to be able to pull the 2 sections apart and have nothing else connecting them. So that's one note about making the cut. And then, so once you identify your zero force members, you have to make sure that you're only cutting through 3 or fewer members that are not zero force members, because you only have 3 equations to use to solve the problem, right? So, and that's because it's a non-concurrent system. So then once you cut it, see if the 2 members that you expose that's not the one you care about have anything in common. So a lot of times they'll be pointing towards the same point. And if you take the moment about that point, you might be able to solve directly for the one you care about, which is the case of what happened in the example problem the day you got your project, right? So they all met at point D. And for that reason, you could take the moment at D and find the internal force in OK because that was the only other unknown. So that's about it that for method of sections. Just remember that it's still an equilibrium problem. Other than that, another reminder of my office hours, here they are. And then I can't help you if you don't ask me for help. So other than that, that's really all I have. And I will hope to see people on Monday for the exam, or not for office hours. And I'll see whoever's in class Monday in class. So there's that. All right. Have a great weekend, guys.